let's start off with a really basic example that we can all understand. So let's say for some reason, somebody wants to create an interpolating polynomial to approximate e to the 1/2 power, all right? Now, most people know that e to the 0 is 1. In fact, that's a pretty basic algebra property. And most of us probably have e to the first memorized as like 2.7182882, okay? Or we've probably plugged in our calculators a lot and played with it. So let's create a linear interpolating polynomial, okay? And what we're going to do is we're just going to use two formulas to get B1 and B2, and we can just program them really easily in Matlab, okay? And then these are going to be the coefficients of the linear association, and we're going to eventually get this, okay? So we could just think of this as our B1 right here, and we could just think of this as our B sub 2, all right? And we could just substitute directly in, all right? So let's just get to it in Matlab. It's actually a pretty easy type of problem. So I'm going to start by defining, I'm just going to call my matrix X1. And this is going to be the points 0 and 1. And I'm going to call Y1 the Y coordinates, which are 1 and 2.718, etc. So let me go back and look. So 2.718282. All right. And so now what we can do is we can start to calculate what B sub naught as well as B sub 1 is. Okay. Now we know that B naught is really just going to be, if we look at our formula, that's just going to be the very first function at the Y value. Okay. So we look back here, and in our linear relationship, we could say B1 or B naught, it doesn't matter. I'm just going to call it B1 is equal to the function at the first value, which is 1. Okay, so now I'm just going to go back to Matlab, and I'm going to say that B sub naught is going to be equal to Y1 and the first element of that. Now B1 is going to be equal to the secant. Okay, so if we go back and we take a look, we're going to have Y2 minus Y1 over X2 minus X1, the slope formula, right? And so let's just go ahead and program that really quickly for B1, all right? And I'm going to call that Y sub 1, 2. And let me start that with parenthesis, minus Y sub 1, 1, all right, divided by X2 minus X1. All right, so I'm going to call that divided by X1, 2 minus X1, 1. All right, so those are going to be our coefficients. All right, and I'm just going to leave these open real quick so that way when we run them, we know what B naught and B1 are. So we can go ahead and compute. All right, I'm going to create a Sims variable as well. And I'm going to call that X. And now what I'm going to do is I'm just going to go ahead and find the equation of the first order Newton interpolating polynomial. So I'm going to call this, let's just call it P1 or F1 in this case. And F1 is going to be equal to B sub naught plus B sub 1 times X minus X1. And that's literally how we get an interpolating polynomial. And so we can say that we can do an F print F. And F print F is going to say that the linear interpolating polynomial is, let's just say %s, because it's a string, and let's call F1. All right. Now we're not substituting anything into it yet because part A just asks us to find B naught and B1. And those are just numbers, okay? So now if I wanted to, I'm going to go ahead later and substitute. So I'm probably going to need like a matrix operator a little bit later. But if I just run it and B naught and B1 are going to come up, then that's not a big deal. Or hopefully they come up. And while it's thinking, here we go. So it gives us this formula, which isn't all that pretty, but it is what it is. Okay, so that's our formula. And later we're going to go ahead and test to what error does this really exist. All right, now I'm going to do the exact same thing for quadratic. So now I'm going to call this x2. And remember, for this time, what we're doing is we're just throwing in another variable into this, or another coordinate. Okay, so we need 3 coordinates to be able to get a second order polynomial. And so we have x1 is e at 0, so x1 is 0. x2 is going to be 1/3. And then finally, we can say x3 is going to be 1, and that's going to give us our y coordinate y3. So let's just go ahead and substitute back in. And we're going to plug this into Matlab. So now we're going to get 0, 1/3 for x and 1. Right? And remember before, we knew that at 0, the exact value was 1. And at 1, it was 2.718282. And somebody off the top of their head knew that e to the 1/3 power was this number, 1.395612. I'm sure we all have that one memorized. So 1.395612. Okay, so now we're going to go ahead and we're going to use the exact same formulas to be able to compute what B0 and B1 are. Okay, so let's just call, now I'm going to start with B1. It doesn't really matter this time. So B1, I'm just going to make that equal to x2, 1. All right, so that's just equal to, I'm sorry, y2 at 1. All right, so that's just equal to our first y coordinate, which is right here. Now we're going to get the secant slope. All right, and that's going to be our coefficient of the linear term. And remember, if we look at our formulas, we can just go right back here to our formulas. And we can see that B2 is going to be y2 minus y1 divided by x2 minus x1. All right, so that's nice and easy. So that's going to be y2, 2 minus y2, 1. And then we're going to divide that by x2, 2 minus x1, x1, or x2, 1, excuse me. All right, so that's our slope for the linear term. And now 3 is going to be a little bit uglier. All right, so we look at our formula and we have this animal right here. So we're going to have y3 minus y2 divided by x3 minus x2. And then we're going to have y2 minus y1 divided by x2 minus x1. And the good news is we just computed that. That's B2. Right? So we could just substitute B2 right in there. And then we're just going to divide all of that by the difference between x3 and x1. All right, so that's not too bad. So let's just go ahead and compute B3. Right? And B3 is going to be equal to, now we're just going to cheat. And we're going to take this slope right here. And we're going to copy it in here, except we're going to use 3, 2, and 3 and 2. Right? And then what we're going to do, by the way, this should be a 1. And then we're going to subtract out B2, which was the previous slope. All right? And then the last thing we're going to do with this, so let me put this out here. So I'll get another set of parentheses because this is all a numerator. So one set of parentheses here, and then we're going to subtract out B2, and then we're going to divide that by x3. So it's x2, 3 minus x2, 1. All right, now, and again, all I did, and I know this looks, it's tough to follow sometimes, but I just use these formulas right here, okay? By the way, this should just be an F, not an F2. All right, so let's go ahead and see what we get out of this, okay? And of course, we need an F-printf statement. I'm just gonna copy this one. And And we need an F2. So F2 is going to be equal to, we have our B1 term plus B2 times X minus X1. Right? So that's, and remember, X1 is going to be defined as X2 first slot. And then we're going to add B3, which is the coefficient, times X minus X1. So that's going to be X2, 1. And then times X minus X2, 2. All right, now we have to be careful because if we're doing any sort of substitutions back in, we're just going to have to go through, and we should probably just use the matrix operator since it's going to be an X times an X, just in case we want to do multiple sorts of associations with this, okay? And then this is going to be the quadratic. Okay, so the quadratic interpolation is now F2. All right, so that all being said, we're going to run it, and we get this ugly thing right here. All right, so we have our linear, and then we have our quadratic. All right, so looks pretty ugly. All right, so let's go ahead now and see what's going to happen if we try to estimate these. All right, so all we're going to do is we're going to substitute. And remember, at the very beginning of the problem, we're trying to substitute and figure out what E1/2 is. So now we're just going to substitute 1/2 back in for X. All right, so I'm just going to go ahead and I'm going to say estimate linear, I'll just call it estimate linear, is going to be equal to, we're going to substitute into F1, we're going to substitute for X, and we're going to substitute 1/2. And let's call it estimate quad. And estimate quad is going to be equal to substitute into F2. We're going to substitute for X, and we're going to substitute 1/2. And let's do an F print F. And we're going to say the linear estimate of EXP 1/2 is %F and \n, and that's going to be slin. And then I'm just going to copy this and cheat, and we'll just say this is now the quadratic estimate, and it's going to be EST quad. All right, so moment of truth, we're going to run it. All right, so now these are our values, and we have no idea if this is even close to right, okay? And we're going to do that in part D as well with this. So now we have two guesses, which are reasonably close to one another, but just because they're reasonably close to one another doesn't necessarily mean that they're anywhere close to right, right? Now, let's do the last part of this, okay? So we can get a % error, okay? So let's say P error lin is going to be equal to the absolute value of S lin minus EXP 1/2 divided by EXP 1/2. And then I'm going to do the exact same thing, except I'm going to say P error quad. So this is % error quad. I'm going to multiply those by 100 in a moment, by the way. So this is est quad. So that's our quadratic estimate minus the actual value. And that's going to be times 100. And this is going to be times 100. Okay, so all that said, let's hope that the quadratic estimate is better than the linear estimate and that they're at least somewhat close to one another. Okay, so F print F, we're going to say a % error of the linear approximation of e to the 1/2 is %F, and we're going to call P error lin. I've got the N here. And copy and paste. And we're going to say the % error of the quadratic approximation is %F, and pair quadratic. All right, moving to truth. Let's run it. All right, and I forgot. For some reason, it didn't bump down a line. That's weird that it didn't bump down a line. So did I use the wrong backslash or something? That's weird. Huh, okay. So the percent error of the linear approximation is about 13%. And if we're using a linear association to estimate an exponential association, that doesn't make much sense, especially around a half. But the quadratic approximation is really, really good. It's right here, it's going to be 0.6749, etc. So that's really cool. All right. If we really wanted to, we could graph these and we could kind of see, very similar to a Taylor series, if we're getting close or not getting close around that point. All right. So since we're not asked to do that, we won't do it. But this is just showing that with just a simple quadratic approximation, we can get within 1% of an exponential estimate. All right. And that's just because we already knew a value that was pretty close. Remember, we already knew that e to the 1/3 was 0.139, and we knew e to the 1st was this value. So we would say, yeah, sure, it's going to be somewhere between these two numbers. Up here, well, somewhere between 1 and 3 almost. All right. So that's why we had a lot more error this time. All right. So it's all good that we can get a linear association or a linear type of Newton interpolating polynomial. We get a quadratic one. But what if we want a higher order, like a cubic or a quartic or something like that, so that way we can make the error even less when we do our interpolation? And that's what we're going to look at in our next section, is how can we extend these?